Okay, now what if we are in a case that the support of our random variable depends on theta? So let's see this example. Consider the observations 0.2, 5.5, and 3.1 and 2.9 randomly sampled from an uniform 0 to theta distribution. Use the MLE to estimate theta. Well, in that case, the PDF of an uniform distribution is 1 over b minus a. B is, in this case, is theta, minus 0 is theta. But this distribution is for edges between 0 and theta. So we have to be careful because in this case the support depends on the parameter that we want to estimate. So if we don't consider the support, we are going to get something like this. If we calculate the likelihood function, that is the product of the PDFs from I equal to 1 until 4 of the PDFs, that is 1 over theta to the 4 and 1 over theta, and that is equal to 1 over theta to the 4. In our second step, the log likelihood is going to be the logarithm of 1 over theta to the 4, and this is minus 4 times the logarithm of theta, right? And in our third step, if we differentiate with respect to theta, this is minus 4 over theta, and we set this equal to 0, and this has now solutions. So here this is problematic because we cannot estimate theta. What happened here? Well, we didn't consider the support of the distribution, and in this case it's important because it depends on the parameter and we want to estimate it. So what we have to do here is first calculate the likelihood function, that is the product from I equal to 1 until 4 of 1 over theta, but for our data between 0 and theta, right? And this is equal to, we have two cases. 1 over theta to the 4 if all our variables xi are between 0 and theta. And in other case, it's going to be 0 otherwise, okay? What we have to do is to maximize, we need to maximize 1 over theta to the 4, while this is important, all the samples, random samples, are between 0 and theta, right? So how to do that? Well, we have that 1 over theta to the 4 gets big when theta gets small, right? A large value for theta is a lower value for this number. And so that means we want theta as small as possible. But the other condition that we have is that we need the smallest theta that satisfies that our random samples are between 0 and theta, right? For all I. So for example, if we are here and we have 0 and we have one value, it's 1, it's 2, it's 3, and it's 4. If we have a value theta here, for example, and we go to the left to a small value for theta, that will be better, right? But if we go until, for example, this value theta, this is not possible because we have this edge for theta that that needs to be in this interval, right? So our theta is going to be actually located here. That means our estimation is the maximum value. In this case, it's 4. Okay, the bottom line is that if the super depends on the parameter of interest, the MLE estimate will be an ordered statistic, typically the minimum or the maximum. For more unordered statistics, you can check the section 3.10 of the textbook. That means the ordered statistics are, we have the minimum, and we have the ordered statistics, and we have the maximum. You can check that if you are interested.